Hello and welcome back to Math Tutorials. Today we're going to be talking about the integral, the definite integral, not the indefinite integral like last time. Uh, so an integral is, you can think of it as like the area of a function. So basically, right, remember the integral symbol is like this, kind of like a little s thing. So if I said the integral of x over 3 from 0 to 6, this describes this image, right? We have, well, let me tidy this up. This describes this image. So we have the integral sign, right? The little swirly s thing. We have the function, x over 3, that's what this is, right? 0, right? 3, 1, 6, 2, right? So this line right here is x over 3. And then we have the starting point and the end point. So we only are worried about the area. By the way, the area is basically implied to be from the function to 0, meaning that it can be negative. Let's say if it was down here, right? This would be a negative area. But this is positive area. So we have from 0 to 6, and then dx tells you the variable that you're doing. Basically, it should match whatever variable is already inside here, because at least from what I've learned so far, this is pretty much just going to be a one variable thing, and it should match. If it doesn't, you probably got to convert some stuff. Um, but that's the general idea, right? It's the area. So another way we can think of an integral is kind of the reverse of a derivative. So in the same way that you have x squared versus log x of oh, this equals y, and then log x of y equals 2, right? I think those are the same thing. Anyways, the same way you have that, right? Exponentiation and logarithms are inverses. You have plus, what did I just do? I changed to eraser. Okay, plus 1 versus minus 1, times 3 versus divided by 3. These are inverses. Same thing with integral and derivative. So that means that if I say, uh, I don't know, oops, okay, so if I say, um, let's say we have, like before, x over 3, right? And we have, let's say we take the integral of this, right, dx. Let's do indefinite integral for now, because that is kind of more what this is talking about. So let's say we have the function, and then let's call this f of x, and then we take the integral of that function, right? And then let's say we take the derivative of that function, so d dt, right? So then we take the integral of the function. This basically, since derivatives and integrals are inverses, or you can think about it as taking a function, multiplying by 3, and then dividing by 3. You're just going to get back where you started. So if you take the function, integrate it, and then take the derivative, differentiate, there it is. You basically get the regular function. And I think this is one of the fundamental theorems of calculus. It's something like this, at least I think. But anyways, that's kind of the basic idea. So I relate this again to that kind of staircase looking thing, right? If you have f of x, and then you have f prime, right, the first derivative, and then you can throw in the second derivative. Up here, you would put the integral. You put the integral of f of x. So let's say I started at the function and I took the derivative. That'll get me to the first derivative. And then derivative again, second derivative, right? Pretty simple. That's what we learned a few episodes ago. Episodes, sure. But if I started here and went to the integral, I would go to, or I integrated, I would go to the integral of that function. So that's pretty basic. But an important thing is also if I start at the first derivative and I take the integral, right, then I would end up at the regular function, right? And if I take the regular function, or the integral function, differentiate and go back to the regular function, it kind of is all on a staircase, right? Integrating goes this way, and differentiating goes that way. So what does that mean? That means that if I'm given some sort of function, right? If I'm given, we have this, let's say we have something like this, right? And we say, what's the area from, let's say 0 to whatever this is. All right, let's say we find this area. Let's say this area is 5, right? The area is 5. If we are told that this is the graph of the first derivative, then that means the value of f of x, right, so this is f prime, the value of f of x is there's a difference of 5 from 0 to whatever this is. Meaning that, let's say, f of 0 equals 0, then f of, let's call this y, f of y is 0 plus 5, right? There's a change in 5. This tells you how much it changes by. Hopefully that was clear. If not, it doesn't really matter because probably no one's going to watch this. All right, so, and again, you can, like I said, you can kind of relate this to area, right? I mean, it basically is area. So how do you find something like that? Well, the whole kind of idea, let's say we're starting here. This is the Riemann sum idea, right? So we're going 0 to 4, right? So for something like this, you can kind of just, oh, it's a triangle, right? So I can do 1/2 times base times height. But for this, it's not so simple, right? Because you kind of have this curve, right? You could do up to here, call this a rectangle, then make that kind of a triangle, right? But it's really not going to work out that well. So the whole kind of idea is you want to split it up into rectangles. So what you do, and you can change how big they are, but let's say we want to split this whole thing into 2 rectangles using the height of the rectangle as the leftmost point, right? So then we do this. And yeah, I think you guys generally kind of remember how to do a Riemann sum, right? This is a left Riemann sum because we're basing off the leftmost point, and this is going to be clearly be an underestimation because we would look at this area and say that this area is the area of the curve, but really we're not accounting for all of this area. Or we could do a right Riemann sum, right? Look at this point, and then look at this point. But clearly this would be an overestimation, right? Because we would look at this whole area, right? And it would say, oh, that's the area approximately of the curve, but we'd be leaving it, or we'd be adding on this area, right? So ideally, you kind of just do super, super small rectangles, right? Because this is 2 rectangles. It's kind of coarse if you want to imagine like that. Ideally, right, you do like super small rectangles, right? These rectangles, actually, they actually don't have to be the same size, but just kind of imagine they are. You want to have super small ones, because then it'll get more and more accurate, right? And the idea is infinite rectangles basically gives you the area, and that's what the integral is. So I think it's worth kind of expanding on this point from earlier. I don't think it was super clear the way I explained it. But yeah, so the area kind of gives you the change, right? So this is the derivative of f, which means, and if you look at the area from 0 to 5 of the derivative, the value is 5, right? The value of the area, which means that f of x changes by 5. Now, if you had something like this, right? And also notice that makes sense, right? Because the derivative is positive for this whole period, right? Which means that f should be increasing, right? It should be going up, and this tells you how much it goes up by. Remember though, this doesn't tell you the starting point. So I said this, f of 0 equals 0. This is basically just me putting a number in. This could be anything, right? This could be, you don't know, because that kind of relates to the plus c that you have to put on the antiderivatives. But anyways, this could be anything. This just means it's going to be whatever this is plus 5, right? The plus 5 is the important part. And that makes sense, right? Because it's positive, so it should be going up by some amount. If it was negative, right? If it was negative, then it'd be going down, which makes sense because the antiderivative is negative, right? Or the derivative is negative. So hopefully that makes sense. If not, ask a question in the comments, and I'll be happy to answer you. Let's see, so I covered, I guess I could go over, I mean, I already went over how to find the integrals using the, well, we're going over how to find the indefinite integral. So if you have the indefinite integral, that means you have something like this, right? But you don't know like from where to where. But basically, if you have the, let's call the indefinite integral f of x, right? If you have f of a minus f of b, that gives you, I believe it's a, b. These might be switched. I can't be bothered to think about it right now. But that basically gives you this. So let's think about what this says, right? This says if you want to find the area from a to b, right? Because this basically means area from, well, area from B to A technically. What you would do first is find the antiderivative, right? And then you would plug in A, you would plug in, right, the latter value, the second value, and then subtract, right, subtract the first value, which makes sense, right? Because you think, start second value, first value, how much are you changing, right? So I believe this is also a fundamental theorem of calculus. And yeah, this is just saying area equals the change, basically. You can think of this whole thing as the change from B to A. And that kind of is what I was talking about over here, right? Just a generalized version. Um, but yeah, so I guess that'll end this video. Let's see what we're talking about next time. Again, if you have comments, or if you have questions, which you probably do if you're actually trying to use this video because I did not explain things very well, then ask me in the comments. That's fine. That's probably the main, strength of something like this is obviously explanations kind of suck and you can find better explanations anywhere, but I can help you one-on-one, hopefully, in the comments below. Fundamental theorem of calculus. I think I went over that. I think. Maybe. The natural logarithmic function, inverse functions, exponential functions. I don't know. Any of this stuff? Oh, slope fields. Sure, I can go for slope fields next time. Why not, right? Next time. Next time. Slope fields. All right. Yeah. All right. See you guys later. Goodbye.